Hi, in this video we learn about Wheatstonebridge. Wheatstonebridge is designed by Charles Wheatstone and it is useful to find the unknown resistance. And generally bridge means it is a logical connection or a systematic arrangement of resistors and cells or sources of energies. Here, if you observe the structure, it consists four resistances P, Q, R and S. They are connected to a parallelogram like structure, and in between a galvanometer is connected and a cell or battery is connected as a power source. And to understand this Wheatstone bridge, you must understand Kirchhoff current law and voltage law. These basics are necessary to understand this, otherwise you cannot do. So if you are not enough confident of Kirchhoff voltage law and current law, once again go to the previous videos and watch them, then come to this video. Now let us analyze this circuit. Okay, here we are giving a power energy source as a E voltage and a current start flowing through this like this, and here if you observe at this junction, current splits into I1 and I2. I1 flows like this, I2 flows like this, and let us assume that a current Ig flows through the galvanometer circuit and I3 is flowing through the resistor Q and I4 is flowing through the resistor S, and finally we'll get current I flowing to the negative terminal of the battery. And here the important thing here is, out of these four resistors P, Q, R, S, one of the resistor may be unknown resistor, because in Wheatstone our aim is to find the unknown resistance. Okay, so one of the resistor is unknown resistor, and one of the resistor must be a variable resistor, and other two resistors may be known resistance. They must be known resistances. So here we see, for the sake of understanding, we assume that Q is unknown resistor, P is a variable resistor. Variable resistor means we can change the resistance of this resistor. R and S are known resistances, but they are constant resistances. Once again I am resisting. Q is unknown resistance, P is variable resistor whose resistance we can change, R and S are constant resistances. Right? We'll be understanding why these are taken later, but let us analyze the circuit. Let us apply Kirchhoff current law at junction B at here. Kirchhoff current law. Here why we are doing all these things means we want to find the unknown resistance Q. Okay, at the end we'll get one balancing condition. From that you can understand. First of all, apply Kirchhoff current law at junction B. Here you see Kirchhoff current law says that the algebraic sum of all the current meeting at any junction equals to 0. We know that incoming currents, they are taken as a positive, and outgoing currents, they are taken as a negative. Here at this particular junction B, I1 is coming towards the junction, so we have taken plus I1. Ig is leaving the junction, we have taken minus Ig. I3 is also leaving the junction, so we have taken minus I3 equals to 0. Let us say this is equation 1. And similarly, let us apply Kirchhoff current law at junction D. At junction D, here we are applying, if you observe, I2 is flowing towards the junction, so we take plus I2. Ig is also coming towards the junction, we take plus Ig. I4 is leaving the junction, we take minus I4 equals to 0. So in this way we applied Kirchhoff current law at junction B and D. Now let us apply Kirchhoff voltage law or loop law to certain loop. Here we take loop A, B, D, A, and in this loop we move clockwise direction in this way. Now we are moving in clockwise direction and our loop is A, B, D, A. So let's start from A to B. As we are moving in the direction of the current, the potential drop will be there and it is taken as a positive. I1 into P. I is a current, P is a resistance. Resistance into current gives us potential at that particular resistor. Right? then A to B is on, then B to D. Here, let us assume the galvanometer possesses a resistance of G here. So potential drop across the galvanometer becomes G into Ig, and it is taken as a positive because we are moving in the direction of the current. And next, we are moving from D to A. Here you observe we are moving from D to A, but the current is flowing from A to D, opposite direction. So here potential drop is to be taken as a negative, right? So here the potential drop becomes minus I to R equals to 0. Let us say this is equation number 3. Now let us apply the Kirchhoff voltage law to BCDA. BCDB. Now here we move from B to C. We are moving in the direction of the current. Again the voltage will be I3 into Q, which is positive. And here from C to D we are moving opposite to the direction of the current. So here there is potential drop becomes a negative. It is a minus I4S. And from D to B we are moving opposite to the direction of the current, and becomes minus Gig equals to 0. Equation number 4. So we got 4 equations, 1, 2, 3, 4. Now here, so our aim is to find the unknown resistance, and to achieve this we need to do satisfy certain condition, that is called balancing condition of Wheatstonebridge. Here for that purpose what we do, in this circuit P is a variable resistor, and we make that by adjusting P we can make potential difference at B and at D are same. So we make VB equals to VD, that means potential difference at B and D are same. We know that generally current flows from higher potential to lower potential, but here you see both the potentials are at the same, so no current flows through this galvanometer. That means Ig equals to 0. This is called balancing condition of galvanometer. Now we made Ig equals to 0. Now let us see how our equations are going to modify in this situation. So consider the equation 1, which says that I1 minus Ig minus I3 equals 0. Here balancing condition Ig equals to 0, then becomes I1 minus I3 equals to 0. So we write I1 minus I3 equals to 0, which implies that I1 equal to I3. So let us analyze this consequence. It says that I1 minus I3 equals to 0. That means I1 equal to I3. So look at the diagram once again. Here I1, I3, Ig is there, but what we made Ig equals to 0. When Ig equals to 0, whatever the current that is coming, here no more division of current takes place, because here this current is 0. So whatever the current that is coming towards the B also goes through Q. So we can say that I1 equals to I3, no more current through Ig. That is the consequence of this. In a similar way, here also in the second equation says that plus I2 Ig minus I4 equals to 0. If you put Ig equal to 0, we'll get I2 minus I4 equals to 0, and I2 minus I4 equals 0, and I2 equal to I4. Here you can see that the current I2 is coming like this, no more current from Ig, so whatever the current coming from I2, it goes to I4. So we can say that I2 equals to I4. So these are the result we got from the current by balancing condition. Now what are the results we are going to get from the voltage equations 3 and 4? Here if you put Ig equals to 0, this total term becomes 0. You will get I1p minus I2r equals to 0. So I wrote I1p minus I2r equals to 0. And in the second loop equation, I3q minus I4s equals minus Gig equals to 0. Here Gig becomes a 0. So we can write I3q minus I4s equals to 0. So we can write I3q equal to I4s. This equation is called equation number 7, and this equation is called equation number 8. So we are simply dividing equation 7 by 8. 7 by 8. I1P divided by I3Q. I1P divided by I3Q and I2R divided by I4S. I2R divided by I4S. So we know that I1 equal to I3 from this. I1 equal to I3 and I2 equal to I4. I2 equal to I4. Here I1, I3 we can cancel it. I1, I3 because they are equal. I2 and I4 also equal. We can cancel out. Finally, we got the equation P by Q equal to R by S. And remember, this is called balancing condition of Wheatstonebridge. So P by Q, R by S. P, Q, R, yes, all these are resistors. So here if you see from the diagram, it says that P by Q equals to R by S. We can write here by just diagram also you can remember P by Q equal to R by S. So P by Q should equals to R by S. This is very important consequence. And using this condition P by Q R by S, here we know that P, we know it is a variable resistor, R and S also known resistors, and you can find Q from this because P by Q equal to R by S. Using this condition you can find the unknown resistance because unknown resistance is only one here. P we know, R we know, S also we know. You can find resistance Q. And this is useful not only to find unknown resistances, and this condition also useful in solving some electrical circuits also. So we will understand one more example how it is helpful in solving electrical circuits. Suppose you are given a circuit like this. Okay, it is just looks like a Wheatstonebridge, but instead of a galvanometer, here we have 100 kilo ohm resistor. The circuit consists 1.5k, 1k, 4.5k, and 3k ohms. You are asked to find out the current flowing through all these branches, and it is very simple to analyze because by looking at this picture, you can say that it is like a Wheatstonebridge. Now, the first thing we do here is we have to verify whether this is satisfying the Wheatstonebridge condition P by Q equals to R by S. Of course, it is applicable for such all figures. P by Q, here I just labeled it as resistor P, Q, R, S, just like our Wheatstonebridge. Now, if you go and find out the ratio P by Q, 1.5k by 1, 1.5k by 1, and R by S, R by S 4.5 divided by 3, 4.5 divided by 3, you will get again 1.5. So P by Q is 1.5k by 1, R by S is also 4.55, 3 means 3 ones are 3 ones are 3 fives are 1.5. So the ratio is equal, P by Q equals to R by S. So here the balancing condition is satisfied. When this balancing condition is satisfied, then no current flows through this 100k ohm. Simply you can remove this. You can remove this and you can redraw the circuit like this. Okay, now it is very clear that these two are in series connection, these two are in series connection, and these two branches becomes parallel condition. You can analyze this circuit very easily. So in this way, if the circuit satisfies this Wheatstone condition, we can analyze it very useful, very easy way and very useful way.